Battery works, rust happens, current flows, but JEE students still get confused in one chapter, electrochemistry. One chapter where electrons move opposite to what many students think. In next few minutes, electrochemistry will become crystal clear from galvanic cell to Nernst equation. Hello students, let us start one short theory for electrochemistry, starting with some important terms which are most important for upcoming concepts. Pay attention, listen and try to make notes along with me so that for upcoming sessions it will be useful. See, some important terms. First I am starting with, I am writing here metallic conductor. Metallic conductors conduct electricity in solid state. Conduct electricity in solid state. At the same time, it is due to flow of electrons. It is due to flow of electrons. Remember, as temperature increases, conductivity decreases here. Why? Why here as temperature increases, conductivity decreases? Reason for that, due to disturbance in flow of electrons. Due to disturbance in flow of electrons because of high temperature, because of vibrational movement. Due to disturbance in flow of electrons, resistance increases. Resistance increases. See here, metallic conductor conduct in solid state. It is due to flow of electrons. As temperature increases, conductivity increases. The reason for that, due to disturbance in flow of electrons, resistance increases. Hence, metallic conductivity decreases. Examples if you see, like what we can consider, like metal wire, copper, aluminium, wires, etc. like metallic conductors. Next, if you move further, electrolytic conductors. Electrolytic conductors, how they conduct electricity? See here, electrolytic conductors conduct in either molten state or aqueous state. They conduct electricity in molten state or aqueous state. At the same time, it is due to flow of ions. It is due to flow of ions. And here if we consider, if temperature increases, here conductivity increases. Conductivity increases. If I consider reason for this, reason for why here temperature increases, conductivity increases, you can consider reason here due to increase in flow of, due to increase in movement of ions or flow of ions. Important. So due to increase in movement of ions, here you can specify the conductivity in case of electrolytic conductors increases. So due to increase in movement of ions. Why it is increasing? Because of higher temperature, higher kinetic energy. So due to which conductivity increases. So basic terms, electrolytic conductors as well as metallic conductors. So electrolytic conductors examples if you see here, examples of electrolytic conductors, like you can say molten NaCl, aqueous KOH, etc. So these can conduct electricity, molten NaCl, aqueous KOH, etc. Next, if you see here cell, before going to that, another important term here which is electrode potential. Another important term which is electrode potential. So electrode potential, what is electrode potential? See here now everyone. The potential difference between see along with me, try to write notes so that no need to revise again from any other textbook. Directly you will get proper notes here. The potential difference between electrode as well as electrolyte. Electrode and electrolyte. Potential difference between electrode and electrolyte is called electrode potential. Simple definition, electrode potential. Then moving to cell. Next term, that is cell. So what is cell? It is the combination of two electrodes. We can write it is the combination of two electrodes or two half cells. It is the combination of two electrodes or two half cells. Just if we combine one anode cathode, we consider it as cell. Or two compartments, one anode half cell, second is cathode half cell, together we refer it as cell, combination of two half cells. So here we are going to see first types of cells. See here types of cells. So what are those? Let us see one by one. Types of cells, first I am taking here electrochemical cell. Electrochemical cell. So electrochemical cell, cell in which chemical energy is converted into electrical energy. Chemical energy is converted into electrical energy. Whereas another type if I see, that is electrolytic cell. Electrolytic cell if I see, here observe it, electrolytic cell. In electrolytic cell, what happens? Here exactly opposite. Here electrical energy, E I am writing here, electrical energy converted into chemical energy. E is converted into chemical energy. In electrolytic cell, electrical energy is converted into chemical energy. So overall, electrochemistry deals with interconversion of chemical energy into electrical energy into chemical energy. Entire electrochemistry based on these two parts: electrochemical cell, electrolytic cell. First, we are going to discuss about electrochemical cell. Then we are going to start electrolytic cell. So overall, what is electrochemistry means here? It deals with interconversion between chemical energy as well as electrical energy. So interconversion of electrical energy into chemical energy into electrical energy is referred as electrochemistry here. Electrochemical cell. So here if we observe it overall, see here electrochemistry, electrolytic cell, electrochemical cell. First I am starting with electrochemical cell. So before going to that, in the electrochemical cell, as it is producing electrical energy, remember here anode is negative, cathode is positive. Important, these two, cathode is positive. But in case of electrolytic cell, anode is positive and cathode is negative. Anode is positive, cathode is negative. So remember these two. Now let us start with electrochemical cell. I am starting with electrochemical cell. Electrochemical cell also referred as galvanic cell. Here I am taking one example for electrochemical cell. The example what I am taking is Daniell cell. Example is here Daniell cell. So in Daniell cell, do you remember anode is zinc, cathode is copper. And then electrolyte for each anode half cell as well as cathode half cell. So overall here anode is zinc, cathode is copper. And solution also present along with it. In anode you will get zinc sulfate aqueous solution, electrolyte. In cathode, copper sulfate aqueous solution, that is present in cathode half cell as well as anode half cell. Okay. Now you see, for example, if I show, see salt bridge as well as anode half cell, cathode half cell representation I showed here. Observe it. Here there is anode half cell. Here there is anode half cell. Here cathode half cell. Anode half cell, cathode half cell. In first beaker there is zinc rod. In second beaker there is copper rod. First beaker there is zinc sulfate solution here. Zinc sulfate aqueous solution present. Here along with copper rod, copper sulfate aqueous solution present. It is overall representation. So externally circuit is completed by external wire. Internally it is connected by salt bridge. So here there is salt bridge. We will see now functions of salt bridge, how it works. Here inside salt bridge we fill electrolyte and we will see how it is filled. Now you see some key points you write here which are useful for us. So key points about electrochemical cell or Daniell cell. So here at anode, see here at anode where zinc undergoes oxidation and forms zinc plus 2 and 2 electrons at cathode. At cathode, zinc at anode undergoing oxidation to get and converted into zinc plus 2. Whereas at cathode, if I see, at cathode Cu plus 2 ions, Cu plus 2 ions from solution, because copper sulfate contains Cu plus 2 ions. These Cu plus 2 ions gain electrons from cathode, undergoes reduction and convert into Cu solid, which is deposited on copper electrode. So continuously, zinc from anode dissolve into the solution in the form of zinc plus 2. In the form of zinc plus 2, it is dissolved into the solution. Other side, that is from in cathode, Cu plus 2 ions gain electrons from wire or from cathode and deposit on electrode. So due to this, what happens here? See, due to this, the concentration of zinc plus 2 ions at anode increases. Here concentration of copper plus 2 ions decreases at cathode, because continuous Cu plus 2 undergoing reduction and depositing on copper from solution, it is decreases. So overall total positive charge in zinc sulfate solution increases. Here if you see, total positive charge decreases in copper sulfate solution. Why total positive charge decreasing? Because Cu plus 2 positive charge moving towards cathode and depositing on it. Hence total positive charge decreases. Whereas in left side anodic half cell, as many number of zinc ions entering into the solution in the form of zinc plus 2, total positive charge increases in ZnSO4. So electrons move from anode to cathode here. You remember here, electron flow from, very important here, anode to cathode. Similarly, current flow. Every time we know current flow, that is exactly opposite to electronic direction. So here it is from cathode to anode. Cathode to anode, important. So here most of the students make mistakes, but you should not make this mistake. Observe it properly. Electrons flow from anode to cathode, current flow from cathode to anode. Now, the role of salt bridge, observe it here. Salt bridge. Let us see here the role of salt bridge. Role of salt bridge. The salt bridge is a glass tube which is filled with electrolytes. So here first of all, glass tube filled with electrolytes like KCl, ammonium nitrate, etc. Here criteria, remember, here criteria for the selection of electrolyte present inside salt bridge: mobility of cation should be equal to anion. Such electrolytes we need to select. At the same time, it should not react. At the same time, mobility of cation should be equal to anion. So keep in mind these conditions here. So role of salt bridge, if you see here, it completes internal circuit. External circuit completed by external wire. So it completes internal circuit. So both these solutions interconnected, completes internal circuit. Next, similarly, it maintains electrical neutrality. Maintains electrical neutrality. Fine. At the same time, along with electrical neutrality, it minimizes liquid-liquid junction potential. Liquid-liquid junction potential. Meaning, see, if there is no salt bridge here, if it is empty glass tube, then what happens? Both these solutions, if it is empty glass tube, what happens here? Both these solutions enter into through salt bridge and get connected with each other here. If they are in close contact with each other, there exists again potential difference, which is again opposite to cell potential, which is harmful for the cell potential overall. So our main duty is to cut the contact of both these solutions by using salt bridge, which is not empty. Inside salt bridge there is electrolyte like KCl mixed with agar-agar gel paste and filled into the tube. So that's why It completes internal circuit, it maintains electrical neutrality, it minimizes liquid-liquid junction potential. Liquid-liquid junction potential means it prevents the contact of both these solutions so that there is no extra cell potential difference developed at the point where both are connected. So it minimizes liquid-liquid junction potential. Overall, you can say it prevents the contact of both the solutions. Salt bridge. Okay. So be clear about salt bridge information, reaction, whatever we mentioned. So cathode anode reaction we mentioned. So if I see now again net cell reaction here, net cell reaction for Daniell cell. I am writing here net cell reaction. So net cell reaction here it is. I am writing directly. If you add anode reaction as well as cathode reaction, it becomes net cell reaction. So zinc solid plus Cu plus 2. Here it becomes zinc plus 2 aqueous plus Cu solid. So here N factor is 2. What is the N is 2 here? Number of electrons involved in the reaction, that is 2. Or you can write it as directly N is equal to 2, meaning number of electrons involved in the reaction during this overall net cell reaction. So if I write Q value, which you studied in thermodynamics, Q is equal to product concentration by reactant concentration, and solids we neglect here, concentration zinc plus 2 by copper plus 2. It is reaction quotient. During galvanic cell, or you can say during Daniell cell, these factors are observed. Number 1, Q value increases because product amount increasing. E cell value decreases. Why it is decreasing? We will see under Nernst equation term. And at equilibrium, Q becomes K. Reaction quotient, Q becomes K. So remember this particular point, very important. Q increases, E cell decreases. At equilibrium, Q is equal to K. How to represent cell here? See. Representation of cell. Close the note and see the cell representation. Representation of cell. So cell representation, first every time anode we show, then salt bridge, then cathode. First anode, salt bridge double line, then followed by cathode. For example, anode how we show here? See, zinc solid, zinc plus 2 aqueous solution, salt bridge, copper plus 2 aqueous solution, then solid. It is overall cell representation. So here we are referring it as anode. Now it is cathode. Middle one is salt bridge. So nothing but salt bridge connecting the both. Salt bridge. Representation of cell. So anode, that is salt bridge followed by cathode. First by default we take it as anode. Next one is cathode. Okay. Next. Let us see here EMF. EMF is also referred as cell potential or cell voltage. Cell potential, cell voltage. So what is EMF, a cell potential, cell voltage? See here. EMF is, it is developed, electromotive force, EMF, it is developed due to potential difference. Due to potential difference between anode as well as cathode. Anode and cathode. Potential difference between anode and cathode, whichever is developed, we refer it as cell potential or EMF. So how we find E cell here? See. This you can represent it like E cell also. E cell. E cell is equal to, even you can write it as E cell also, cell potential EMF. E cell is equal to higher potential minus lower potential according to IUPAC representation. Higher potential minus lower potential. So EMF are nothing but E cell, higher potential minus lower potential. See, if you are writing anywhere like E naught cell is standard form. It is standard cell potential, which we represent like standard cell potential measured. When we consider standard cell potential, we call it as standard cell potential if we measure it at the particular conditions. What are those? The standard conditions here: 1 molar concentration or 1 atm pressure, 1 molar concentration, 1 atm pressure, and 25 degrees Celsius temperature. Generally we consider these conditions: 1 molar concentration, 1 atm pressure, 25 degrees Celsius temperature. These are standard conditions. So for example, E naught cell, if I take E naught cell is equal to, in different ways you can calculate. For example, if I take reduction potential, if I use reduction potential Rp or standard reduction potential SRP plus oxidation potential SOP, standard oxidation potential SOP. So once formula number 1 you see here, E naught cell you can calculate by using E naught SRP plus E naught SOP. What is SRP? Standard reduction potential. SOP is standard oxidation potential. Or you can calculate like this: E naught cell is equal to, if both are reduction potentials given, then what we do here, both are in reduction potential, SRP of cathode, because reduction occurs at cathode, and similarly E naught SRP of anode. Why we are writing cathode minus anode? Because reduction potential is higher at cathode. Higher minus lower every time we consider. Similarly, E naught cell is equal to, if they provide oxidation potential value, as we know oxidation occurs at anode, so anode minus E naught SOP of cathode. Anode minus cathode. So in 3 combinations you can calculate the given E naught cell value. So observe it properly. It is most important for entire chapter. Most of the students make mistake here. Be clear about this particular concept. Anyway, questions we'll do later after completion of part 1 one shot theory of electrochemistry. All numericals will be covered in the part 2, that is one shot numericals based on electrochemistry. Okay. See now. Once after knowing these combinations, a difference you see here now. If you are writing anything like A giving A plus 3, here it is solid, here it is aqueous. So we consider it as oxidation potential. Why it is oxidation potential? Because charge, it is undergoing oxidation. We refer it as oxidation potential E. If you had E naught, standard oxidation potential. If I am writing same like this, A plus 3 aqueous and A solid, which we call it as reduction potential. Reduction potential. Same if you take standard conditions, standard reduction potential, standard oxidation potential. Here. You write here one important statement. So E naught cell is, here you can say EMF or E naught cell. E naught cell is maximum work done. E naught cell is maximum work done by this cell. E naught cell is maximum work done by this cell. At the same time, it is potential difference between, already we mentioned, or you can say it is responsible for steady flow of current. It is responsible for steady flow of current because of difference in potential, steady flow of current in this cell. Important, steady flow of current in this cell. Yes, observe the note and close the note. Next, moving further, relation between Gibbs free energy and EMF of cell, or you can say E cell. Relation between delta G and E cell after closing the note. So already we know from thermodynamics, delta G is equal to, here we are adding minus NF E cell. So derivation not in syllabus, J is syllabus, directly you can remember the formula. Delta G is equal to minus NF E cell. So what is here F? 1 F is equal to 1 Faraday, which is 96,500 coulomb. 1 F it is 1 Faraday, 96,500 coulomb, which is equal to charge of 1 mole of electrons. So if we refer it, delta G minus is equal to W max, useful work. Meaning decrease in free energy is equal to maximum useful work. Decrease in free energy is equal to maximum useful work, Gibbs free energy. Or you can say here useful work means like electrical energy. So W max is equal to, you can write it as NF E cell. W max is equal to NF E cell if you remove negative sign overall here in this case. Okay. Relation between delta G as well as E cell. Delta G is equal to minus NF E cell. Next, properties of delta G. Properties of delta G and delta E. Or you can write it as E cell. Delta G, or you can specify it as E cell. So what we are going to do here, see, property number 1. If reaction is reversed, then if reaction is reversed, delta G2 is, assume that delta G1 is X. So delta G2 after reversing the reaction becomes minus X. Similarly, if E1 is X before reversing the reaction, after reversing the reaction it becomes minus X volts after reversing the reaction. If two reactions are added, what we do here? If two reactions are added, then delta G3, you can write it as delta G1 plus delta G2. But E3 is not equal to E1 plus E2. E3 is not equal to E1 plus E2 because only for redox reactions directly we can add. Other than redox reactions you cannot add. Remember, E3 not equal to E1 plus E2 only valid. And remember, E3 is equal to E1 plus E2 for redox reaction only. For redox reaction only. Remember the condition. Rule number 3. If reaction is multiplied by n number, reaction is multiplied by any number that is n, think that, then delta G2 is equal to, think that if delta G1 is X, you write like this, delta G1 is X, so delta G2 is n X we write. But for E2, but for E1, for example, if it is E1 is X volts. If reaction is multiplied by number n, then for E2 we write X volts only because it is intensive property. Because reason here it is, reason why we are showing different for E. So remember, E cell is intensive property. What is intensive property? Which is independent of mass. It is intensive property. Intensive property, so which will not depend upon mass. Whereas delta G, gives free energy, is an extensive property, which is an extensive property which will not depend upon, which depends upon mass or size of the system. Reason why we are writing different properties for both of these. Okay. Next you see Latimer representation. Next topic, Latimer representation. Every topic we are going to cover. So watch carefully. Your concepts will be crystal clear after completion of entire electrochemistry. Latimer representation. For example, if I take one example, Cu plus 2, Cu plus, here Cu given. See, all are reduction. Here it is reduction process. For example, standard form. Here SRP value I am taking here. Here also SRP value. Okay. Why we are using Latimer representation? Whenever, if SRP of right side greater than left side, which is right side, which is left side, see here, SRP of right side, if it is greater than left side SRP, then middle ion that is Cu plus 1, Cu plus, that is middle ion, undergoes disproportionation. What is disproportionation? Same element undergoes both oxidation and reduction. So SRP of right side value, if it is greater than left side value, then middle ion undergoes disproportionation reaction. To find it, we use Latimer representation. So remember the sequence what we used here. Next moving further, the highest weightage from this chapter, that is Nernst equation. Highest weightage, which we call it as Nernst equation. So most of the topics related to Nernst equation in this chapter. So keep heading Nernst equation. Okay. See now Nernst equation. So what is the use of Nernst equation? See here, used to calculate EMF or E cell for given concentration and pressure. Used to calculate EMF for given concentration and pressure, Nernst equation. So how we are getting Nernst equation? See here. According to thermodynamics, delta G is equal to delta G naught plus 2.303 RT log reaction quotient, that is Q. RT log reaction quotient, that is C here, log Q. So here delta G we know, we can write it as NFE cell without any naught because standard form is naught. Here NFE naught cell plus 2.303 RT plus 2.303 RT log Q. So it is over after substitution of values. What I am doing now, divide equation by minus NF. Divide by minus NF. So if you are dividing by minus NF, what we are going to get here? E cell is equal to E naught cell minus 2.303 RT by NF log 10 Q. Log 10 Q. So what are the values here? Here values like R is 8.314. Here R is equal to 8.314 joule per mole per Kelvin. Temperature is, which temperature we take here? 25 degrees Celsius, which is equal to 298 Kelvin. In Kelvin we have to substitute in the given information. Faraday, that is 1 Faraday is 96,500 Coulomb. After substitution of all these values, here we are going to get E cell is equal to E naught cell, which is in standard form. After substitution of all values, if we calculate N log Q. So it is our required Nernst equation after adding all these values. So remember, it is Nernst equation after adding all those values. Nernst equation, very important with high weightage. Okay, see here, first I am taking here case 1. Case 1, if cell is at equilibrium, then how we can modify Nernst equation? See, if cell is at equilibrium, then you can write, see, according to Gibbs free energy, if cell is at equilibrium, delta G is 0, then E cell becomes 0 because delta G is equal to minus NFE cell. That's why E cell becomes 0. If you substitute same in above equation, what you will get now? E naught cell is equal to plus 0.0591 by, see what is N here? Number of electrons involved in the reaction. At equilibrium, what we write? In place of Q, we write here KEQ, that is equilibrium constant. That is case 1. Similarly, if I take case 2, when we write case 2, that is if cell is concentration cell. If cell is concentration cell. So what is concentration cell here? Concentration cell where both half cells are made up of same material. Both half cells are made up of same material, but there is concentration, but different concentration. Such cells are concentration cells. So, for example, you see, I am giving one example. Here there is zinc plus 2, salt bridge, zinc plus 2, zinc solid. Here concentration is C1, concentration is C2. C1 not equal to C2, concentration different. Such cells are concentration cells. See, whenever concentration cell is taken, then E naught cell becomes 0. E naught cell becomes 0. If E naught cell is 0, then how we can modify the equation? Then we can write equation, Nernst equation as minus 0.0591 by N log C1 by C2. It becomes C1 by C2. Overall, what is C1 here? C1 is concentration of, it is concentration of anode. Concentration of anode. Here concentration of cathode. Concentration of anode, concentration of cathode. Okay. So now here, for a cell to be spontaneous, conditions you see here now. For a cell to be spontaneous, remember delta G should be negative, E cell should be positive, or you can say here C2 should be greater than C1 for spontaneous process. For spontaneous process, these conditions are necessary for us. Okay. Next moving further, reference electrodes. Reference electrodes. See, reference electrodes are standard electrodes. Mainly these electrodes are used to measure potential of other electrodes. These are standard form. Like in titration, we use one solution whose concentration already known to us, by using which we calculate other concentration. So used to measure potential of other electrodes. Such two examples we are going to see under reference electrodes. First example, which is hydrogen electrode. So here hydrogen electrode, first standard reference electrode. Let us see here. In hydrogen electrode, three components present. Contains three components. One, it is H2 gas, H plus aqueous solution, and platinum wire. Platinum wire here used as charge carrier. It will not participate in the reaction, just acting as charge carrier, platinum wire. Okay. So first, if I take case 1 here, case 1, see standard conditions if you use, what are the standard conditions here? Case 1, SHE, standard hydrogen electrode as anode. So what are the standard conditions? So remember, standard condition, partial pressure of H2 should be 1 atm, temperature should be 25 degrees Celsius, and H plus ion concentration should be 1 molar. These are standard conditions. Now, so under such standard conditions, hydrogen electrode, which we refer to as standard hydrogen electrode, used as anode. So if it is used as anode, the representation you see here, reaction you have to remember. So here you can write like H2, which is gas, giving 2H plus and then 2 electrons. Or you can write even like this, half H2 giving H plus electron. So representation you see, how we represent SHE as anode, you see representation, we show like this, E naught, standard form, platinum solid, and then as it is anode, which process occurs? Oxidation. So H2 zero state converted into H plus aqueous state. So which is representation for anode, because it's 0 converted into plus, you see here 0 converted into plus 1. That's why it is oxidation representation. So reaction also here we know, by using which we can write even Q value. So how we can write Q value here? Q is equal to, Q value is H plus ion concentration by, here if you consider this reaction, below reaction, H plus ion concentration by partial pressure of, I am writing clearly here, see here I am writing Q is equal to partial pressure of, first of all, concentration of H plus, because product by reactant we write, by partial pressure of H2, where power is half. By using this reaction I wrote, or above reaction also you can use. Nernst equation you see now. So here oxidation potential, which is OP, is equal to standard oxidation potential minus 0.0591 by N is 1. I am taking below equation, N is 1, log 10. So which is Q value, H plus aqueous by partial pressure of H2, which is half. So it is equation for anode representation. Similarly, I am writing for cathode. Case 2, standard hydrogen electrode as cathode. Same representation. As it is, we are going to write, just comparison, see here now. If you are using it as cathode, reaction you see here, H plus aqueous gaining 1 electron converted into half H2 gas. So Q value if we write here what you will get Q value, first partial pressure of H2 half by, at the denominator we will write H plus ion concentration. Representation of cathode, that is SHE, how we represent? E naught H plus aqueous by H2 gas and platinum solid representation like this. So if I show here now E of RP reduction potential, E naught SRP standard reduction potential minus 0.591 by 1. Here also you can write n value 1 log base 10. So here Q value partial pressure of H2, which is half by H plus ion concentration at the bottom. So see the equation here. Here also we mentioned it is equation for anode. Below one there is equation for cathode. Important, by using which we are going to calculate many calculations, many questions. Okay. I hope no doubt till here. Next case you see. Next case, case 3. You see here case 3. So case 3 is SHE, or if I write, simply write hydrogen electrode as concentration cell. Hydrogen electrode as concentration cell. So hydrogen electrode as concentration cell, if you represent first equation, see I am writing here platinum solid, where H2, first I am writing anode representation, H plus salt bridge, H plus H2 platinum. Respective information I am writing here, see here P1 concentration C1, concentration C2, H2 P2 ATM. In both the cases it is solid only here. Okay. So if concentration cell, we already wrote anode cathode reaction, right? I am writing directly now net reaction. Net reaction how we write? Adding both anode as well as cathode. So net reaction if we write half H2 plus H plus, here giving H plus, then half H2. Which one? Carefully observe it. Here it is for anode. I can write it as P1. H plus there is for cathode, which is C1. H plus again, it is for anode, which is C2. It is for cathode, H2, which is P2. So now if I write in Nernst equation, if I put in Nernst equation here, as it is concentration cell, right? So concentration cell, what is E naught cell value? For concentration cell, E naught cell value is 0. If I put in Nernst equation here, so here you are going to get E cell is equal to 0 minus 0.591 by 1 log C1 P2 by C2 P1. For P2 here it is half, P1 also here half. C1 P2 by C2 P1 half overall. Okay. So first we got one important conclusion. If you use hydrogen electrode as concentration cell, this particular equation will get here in this case. Look at the equation everyone. Okay. So and based on this, if P1 is equal to P2, I am taking here one condition and we'll see what happens here if we take this condition. If P1 is equal to P2, if I take this condition, if P1 is equal to P2, then what we can write here, E cell is equal to, in question if they provide P1 is equal to P2, then directly we can write 0.0591, that is 1 log 10 C1 by C2, C1 by C2, right? C1 by C2 meaning what we can write here, E cell is equal to minus 0.0591 log 10. So concentration of H plus of anode, H plus of cathode, H plus of anode, H plus of cathode. So if I modify further, as we know minus log H plus is pH. So if I do further here, you are going to get 0.0591. Here you can write pH of anode followed by pH of cathode. So one important conclusion we got, the final direct formula you can use here, pH of anode minus pH of cathode. When it is valid? It is valid only if P1 is equal to P2, you can use direct formula pH of anode minus pH of cathode, right? So here if you remember one important note with respect to spontaneous, non-spontaneous reaction, if pH of anode is less than pH of cathode, pH of anode is less than pH of cathode, then E cell is equal to then E cell is equal to negative. pH of anode less than pH of cathode, then E cell is negative. Then reaction is spontaneous, non-spontaneous. Reaction is non-spontaneous. When reaction is spontaneous if E cell is positive. If reaction is positive. Okay. Another case I am taking here, see. If C1 is equal to C2, another condition, if C1 is equal to C2, then what happens here? E cell is equal to minus 0.0591 log P2 by P1, each we can represent like half, right? P2 by P1. So if P1 is greater than P2, then E cell is positive, cell reaction will be spontaneous. Then reaction is spontaneous. See, observe it. Overall, hydrogen based concentration cell we used here, C1 is equal to C2 on respective information. Again, one more important case here. If, see, reaction we can specify like this: P2, H2, HCl, salt bridge, HCl if I take, and then H2SO4. Both are strong acids. Both are strong acids here. If strong acids taken, no need to think about it. Directly you can follow concentration, C1, C2 information based. But if weak acids taken, if weak acids like CH3COOH taken in place of strong acids, then how we use formula here? Directly you can't get C concentration of weak acid, directly can't calculate. We need alpha also. For that, if weak acids like CH3COOH taken, then what we do here, in such cases, E cell is equal to minus 0.0591 by N. How we will get here? Log concentration like Ka1, acid dissociation constant 1 by concentration 1 by acid dissociation constant 2 by another acid into C2. Which one? The above one is, it is for anode, it is cathode. When we use this formula, Ka1 into C1, if it is weak acid, whenever weak acid is given, directly use this formula. Ka1 C1 by Ka2 C2, anode as well as cathode. For weak acids, directly you can use this formula. Okay. Next reference electrode. Here you see above what we discussed. Reference electrode 1, that is hydrogen electrode we discussed. Now I am considering here reference electrode 2, which we call it as a calomel electrode. Calomel electrode. Here you write one important point. SRP as well as SOP of hydrogen electrode, very important. SOP and SRP of hydrogen electrode, as we get negligible potential from these hydrogen electrodes, is assumed as 0. Based on negligible potential, they assumed overall SOP, SRP of hydrogen electrode is assumed as 0 because of negligible potential. So directly we will consider it as 0 here. Okay. And then moving to calomel electrode. So calomel electrode here, same, one of the reference electrodes. Calomel electrode, first I am directly taking here case 1. Calomel electrode as anode. Here also 3 components present. We will see those components here directly here itself. So as anode reactions, observe it. There is mercury which is in liquid state plus 2Cl minus aqueous form. Calomel is the common name of Hg2Cl2, which is solid plus 2 electrons. So it is calomel. So here if you are writing Q value for this, so what we write here, Q value 1 by Cl minus, solids and liquids will not write, so 1 by Cl minus 2 here as anode. Similarly, case 2, calomel as cathode. So just we are changing the reaction. So cathode representation if you see, so how we can write cathode reaction? Hg2Cl2 mercurous chloride, which is solid form, gaining 2 electrons and forming 2Hg, which is in liquid form, plus 2Cl minus. So Q value, how we write? Concentration of Cl minus whole square, Q value. So based on that, you will get SRP, SOP values representation. So anode representation, cathode representation, you see here. Anode representation of calomel electrode. Okay. Anode representation, I am writing here for calomel electrode. How we write? Anode is platinum solid, Hg liquid, because mercury from 0 state to Hg to Cl2, it is converted. That's why first we are writing, then Cl minus aqueous. Anode representation. Similarly, you write for cathode. Cathode representation. What we show here? Cathode representation. Cl minus, which is aqueous, then Hg2Cl2, which is in solid form, then followed by Hg liquid, and last we show here platinum solid. So Hg2Cl2, what is the charge here? Charge overall it is +2 charge. Here 0. 0 to +2 oxidation, anode. +2 became 0, reduction, cathode. Anode, cathode representations we specified. Okay. So that is about difference electrodes like hydrogen electrode as well as calomel electrode. So it is part 1 of electrochemistry. We know electrochemistry is very big and high weightage chapter for JEE advanced exam. Even for JEE mains exam is bigger chapter. If I complete entire chapter in one single part for this chapter especially, it's not so clean. It will not cover entire all concepts. Just I am giving part 2 for this, where electrolytic cell will be discussed in detail. Okay. I hope all the concepts clear to each and everyone. Part 2 will be continued after completion of part 1. Okay. Thank you. Thank you very much.